Hello and welcome back as we continue our journey into intermediate Java. We're focusing in on data management. We've looked at files. We've looked at being able to evaluate the efficiency of algorithms using big O notation. And now we're focused in on searching. And today we're going to look at three methods of doing searching, and we're going to evaluate each of them a little bit. And we're going to start off with the simplest type of search. You did this in your first programming course when you looked at looping through an array. You did something of this sort. And so here's an example with cards. I have a number of cards laid out, and let's say I'm looking for the 10. Well, what I could do is I could start over here, and I could keep looking one card at a time until I find the 10 of diamonds that I'm searching for. And so I'd start here with the jack, I'd come over to the 10, I'd find it. And so I've done two operations, two checks in order to find the item that I'm looking for. Of course, as we've discussed, you could be really lucky and you could get it right away, or you could be very unlucky and you're going to have to go through all n of the cards in order to find the item that you're looking for. This has a technical name. It's called a sequential search. And the sequential search is essentially the for loop that you have used. And that is, you start at the first item in a list or an array, and you keep looking for the item that you're searching for, and you might get to the end and not find it, or you might get to the end and find it at the very end or at the beginning. And based on the discussion that we've had, I hope you can see that what we're looking at is a linear algorithm. This is an algorithm that as your data gets bigger, you are going to be doing more searches, but not proportionally more searches, just keeping in line with that. What you can also imagine is that when you get to something like a dictionary that has 1.2 million words of text, that this algorithm could potentially have to make 1.2 million comparisons in order to find the word that you're looking for. And that could be rather onerous. However, linear is within the powers of a computer to deal with. Another view of how that works is with a Java kind of bent here, is that here you have your array. Array start, of course, at 0. You have a for loop that's going to start at 0. It's going to go to the length of the array. And if you and you're going to just kind of go through and find the item that you are looking for. And that's essentially the way that a sequential search works. And that's fine. There's a reason why you've used for loops to go into arrays up until this point, and that's because for most of the sizes of data that we're trying to work with, it's reasonable. But there is a faster way of searching through data. And so you can see it a little bit more if you look at this set of cards. And imagine that I was looking for the queen. So if I was looking for the queen and I was doing it in a linear fashion, I would have to search 1, 2, 3, 4, 5, 6, 7 times. If we switched our algorithm a little bit, and instead what we did was we keep looking at the middle card in our set of cards. So the middle card in this case would be the 10. There's 4 cards on this side, 4 cards on this side. I look at the 10 and I say, is the queen going to be bigger than this, or is it going to be less than this? It turns out that the queen's going to be bigger. So that means that I can get rid of, let's physically get rid of these pieces of nonsense. I can get rid of all of these cards with just one check. And now I'm only looking at these cards over here. So I look for the middle card. In this case, I'll round down. And the next card I look at is the queen, which happens to be the card that I'm looking at. So that means in 2 operations, I have been able to successfully find the card that I'm looking for. Now, let's imagine for a moment that instead of the queen, I was looking for the king, or even, let's say, the ace. So in that case, my second operation would have been to check on the queen. I would have said, oh, no, the ace is bigger. So now I would have cut off, and I would have had this subset to look at. My third operation would have been, oh, okay, let's check the king. And my very fourth operation would be to find the ace. That means that this is the worst possible scenario I've got here, and yet I'm still being able to accomplish it in only 4 moves, as opposed to linear, where I would have to do 1, 2, 3, 4, 5, 6, 7, 8, 9. That is a huge savings, and it turns out that this is a logarithmic efficiency. That's what we talked about before, cutting away half of your cards, or roughly half of your cards, every single time. And this algorithm is also going to have a name, and because we're cutting half-C's, 2's, it's called a binary search. And the binary search is literally what we talked about, finding the middle term. Here, let's actually look at it in a different way. Finding the middle term, so here's an array, finding that middle term, and then either choosing one half or the other half to look through. Then once we get to this, we look at that middle term again, and we either go to split one way or we split to another way. And you'll see why it's called binaries, because we're branching into 2 every single time, and the logarithm is related to exponents. It's kind of like the opposite operation. So every time we choose a branch, we're cutting down the size by half, by half, by half. That is fantastic. It shares the same best case scenario as linear, but the worst case scenario is much, much less, because you have much less to go through. So with all this data here, what is that? 2, 4, 6, 8, 10, 12 different pieces of data. At most, I'm going to be searching through 1, 2, 3, 4. At most. So binary search it turns out, gives you a lot of savings, but there's a cost to it, right? Remember that Big O only looks at a very small subset of the things that you need to worry about. It just looks at operations, right? The algorithm is more complex. Linear search is just a single for loop. It's nice and easy. The algorithm for a binary search can look differently in different ways, but it's a little bit more complex. You still have a loop, but now you have to calculate a middle point. You have to evaluate that middle point, and you need to change what part of the array you're looking at. So first you're looking at the whole array from low to mid, from low to high. But then at some point you look at the middle, and then now you're going to have a low and a high of only this point. Then you're going to cut it again, and you'll have a low and a high, and you'll cut it again and cut it again and cut it again until you get to just that item that you're looking for. And that's what's happening here, is that we have a low variable, which is representing the lowest part of the array that I'm currently looking at. You have a high, which is looking at the highest point of the array that I'm looking at. And then you have a middle, which is that middle point. And so your low and your high are going to keep shifting until you get to that one point. What if the item doesn't exist? Well, eventually you're going to get down to just one item. And if it's not that item, then you're going to know that it's not in the list of what you're searching for. So binary search is great. But some of you might have noticed that I pulled a little trick on you. There was a difference between this set of cards and this set of cards. And it's a really important difference. And that is that this is sorted. Binary searching only works if your data is sorted. If your data is not sorted, you are in trouble. You are potentially in big trouble, because let's say, for example, I am looking, in this case right here, for the 3. And I want to do this in a nice, efficient binary manner. So the first thing that I do with my first operation is I come right over here to the middle, and I say, okay, is 3 bigger than the queen, or is it less than the queen? And guess what? It's less than, which means I'm going to now search in this section over here. But wait, the 3 is over here. So what that means is I'm not going to find the data that I'm looking for, because this isn't sorted. So there's no question that binary is more efficient. But if your data is not sorted, you have to also think about the cost of sorting your data before you do a binary search. And in some cases, that's easy to do. In databases, you can constantly kind of reorganize your database to make sure that as you add new items, it stays nice and sorted and you can make efficient searches. But in most practical cases in the computer that we've come across so far, with small bits of data and small arrays, it's not worth the effort to sort them. So overall, which one is superior? Well, when n is small, there's no difference, especially given how fast the computer works. There is really no difference. When your array gets bigger, there's no question that the binary has better performance. But remember, you do need to have your data sorted in order for it to work. Okay. To give you an example of just how many operations you could be saving, if I had 2 million entries, the logarithmic efficiency would require no more than 30 comparisons. There is one other algorithm that I wanted you to be aware of. We're going to talk about it again when we get to sorting, but it's called hashing. And hashing can potentially offer better than binary efficiency in some situations, in some data, some sets of data. And the way that it works, the best way to describe it is that you use some sort of a key to help you categorize or sort your data. And anyone who's ever played bingo, okay, if you haven't played bingo, I'll give you the quick synopsis. There are 75 numbers. Numbers 1 to 15 can show up here, and then 16 to 30 show up in this column, and then so on and so on and so on, going by 15s, 15s, 15s. The way that hashing works is you use some sort of a key to determine which category your data will fall into. And so, for example, if I have the number 14, I know that the 14 has to fall under B. Now, why is this potentially better than linear search? Well, remember, linear search can only cut off half of your data at a time. With hashing, if I am looking for the number 12, and that's why, if you ever played bingo, they'll say B12. And the reason they say B is because B is telling you which column to look for. And what that means is that I'm able to not worry about any of this other data inside here. That's more than cutting in half. I now only need to worry about this data here to look for B8 or B12. And so hashing has the potential, if you use the right sort of hashing key to break things down, has the potential to be very good. Now, what if instead of having this random, I now made this subset binary, like sorted? Then I would be able to use a binary search in this smaller subset to make my efficiency even that much better. Now, as you might have guessed, how efficient this is depends on how good a key you use. I mean, if every letter here had only one number associated with it, then I would basically have to have 75 different buckets, which wouldn't be any more efficient, right? It would actually be making things worse. So you want to try to find a way to make good sized buckets to collect your data. And so that would be how hashing works. And you'll notice that the searching is only part of it. You also need to figure out how to sort it using the key in order to get that structured data to make your search that much more efficient. So that's it. We've talked about 3 different ways of searching. We talked about linear, we talked about binary, and we talked about categorizing into buckets using hashing. We've also talked about the relative efficiency of each. Linear, okay. Binary, better. Hashing, it depends, right? It depends on how effective your hashing algorithm is when you're creating your buckets using this key. Has good potential. So our next topic is going to be sorting, but until then, enjoy some coding.